Okay, we're going to practice with some example about the electron configuration. Now, before starting with some practice, we have to know about these shell, subshell, orbital. First of all, we have to know this is the distribution of the electron outside the nucleus. Okay, so here we will have the nucleus, the proton plus the neutron here. The outside, it is the electron. First of all, here we have the level of energy, which we call it the main shell or the principal level of energy. N equal 1, then 2, then 3, 4, and continue. And inside each shell, we have subshell. So for example, in shell number 1, n equal 1, we have only one subshell. And n equal 2, we have two subshell. And 3 equal 3 subshell, and 4 equal 4 subshell. Usually, the number of subshell equal the n value. So if I have n equal 5, that means I have 5 subshell. Now, for each subshell, we have letters specified. So for example, for n equal 1, we have just one subshell, which is the S subshell. N equal 2, we have two subshell, S and P. In 3, we have SPD. In 4, we have SPDF. Now, in each subshell, we have a specific number of orbitals. So let's go look here. So we said in each subshell we have a specific number of orbitals. So in S, always one orbital. P, always 3 orbital. D, 5 orbital. F, 7 orbital. And you have to keep in your mind, it doesn't matter if we have 1s or 2s or 3s or 5s or whatever it is. And as always, we have one orbital, just one orbital. P, always a 3, the same things. 2s, 3, 2p, 3p, 4p, 5p, whatever it is. P, always a 3. D, 5 orbital, 7, it is 7. Sorry, F, it is 7 orbital. Don't forget, always in each orbital, the maximum 2 electron, the maximum will be 2 electron. Could hold 1 or 0, empty, 2, but not more than 2 electron. So also you can say here, for example, S, the maximum 2 electron. P, 6 electron, because the 3 orbital times 2. 5 for D, so it will be 10 electron. 7 orbital for F, so it will be 14 electron. Okay. You have to know we have the electron configuration in a ground state, which is the one that we will focus on it, and we have excited state. The ground state of the electron is the lowest energy orbital it can occupy. Excited state when an electron moves to a higher energy orbital. Here also can give you this table, how many subshell, how many orbital we have, and the maximum of electron in each shell. So for example, in shell number 1, the maximum of electron 2. Shell 2, the maximum 8. Shell 3, the maximum number of electron in that shell, it is 18. 4, 32. You can do it according to this equation. the number of maximum electron will be 2n squared. So for example, if you have n equal 1, so it will be 2 times 1 square, and it will be 2 electron. If we have n equal 2, so it will be 2 times to power 2 and equal 2 times 4, multiply, and that will give you 8 electrons. N equal 3, so it will be 2 times 3 to power 2, 3 square, and that will give you 2 times 9 and give you 18 electrons. Okay, and this is the number in each subshell, the maximum number, S2, P, excuse me, P it is 6 electron, and D it is 10 electron, F 14 electron. Okay, electron configuration show the occupation of orbital by electron for a particular atom. Electron configuration for ground, say for hydrogen, it is 1s1, for example, because we just have one electron. So this represents the orbital. This is the orbital. And here, this number 1 represents the number of electrons in the orbital. Now, you have to know how we will figure out the correct order for the orbital that will be filled. So be careful. You will start with the 1s. It is the lowest energy orbital. So 1s, then you will go, just follow the order, follow the arrow, then 2s, then after 2s we have 2p, and 3s, 3p, and 4s, 3d. So be careful, look at here. We will fill the 4s before the 3d. Then we will fill the 4p. 3s, 5s, 4d, 6s, then 4f, then 7f, and 5f. You can just write, for example, n equal 1, n equal 2. We have these, n equal 3. Here you have these instruction how you will add out this. This is n equal 4, n equal 5, n equal 6, n equal 7. And then you will just draw this arrow to figure out the correct or the correct order to fill this orbital. Okay, how you represent the electron configuration? Either by orbital notation, which is you will use the orbital boxes, and inside the boxes you will just put these electron, how many electron, and don't forget, sometimes, by the way, you can do it half arrow or whole arrow, but inside the boxes is supposed to be opposite in the spin for these electron in each box, which represent orbital. Electron configuration, the complete electron configuration notation, you will just replace these boxes by how many electron as a superscript for the subshell. So it will be 1s, we have 2 electrons, so it will be 2. 2s, 2, 2p, 3. Okay, and continue. We have some rule, you have to keep it in your mind about principle, the Pauli exclusion principle, and so on. Quickly, with these. Electrons are lazy. The above principle, electrons are lazy, so they will fill the lowest energy. So you will start from 1s, fill it, then go to the 2s, fill it, then go to the 2p. That's how you will fill. Okay, what else? Pauli exclusion principle. The maximum in each orbital will be, in each box, will be 2 electrons, and they have to be opposite in the spin. One of them spin up, the other spin down. Okay, what do we have here? Hans rule. We have, for example, more than one orbital in that subshell. You will start to half fill first, then full fill. So look at here. I just have 1s, just one box in that subshell. So fill it. 2s, just fill it, one orbital. But to look to 2p, I have 3 orbital. So here in this situation, I will half fill first, then you will start to fill. Okay? Don't do it like this way. It's supposed to be half filled, then fulfilled. This is a very important rule. Excuse me. Now let's start with some practicing for the atom. So look at here, so this one. Okay, let's start with electron configuration for some atom. Hydrogen, let's start with the summary. How many electrons for hydrogen? Look to the atomic number of hydrogen, and it has 1. So the number of electron, it is just 1 for the hydrogen. We will start with 1s. We have 1 box, so you will put just 1 electron. Arrow or half arrow. This represents the electron configuration orbital diagram. We call it orbital boxes diagram. The complete electron configuration notation, we will just replace the box by a number, how many electrons we have in that box. We have 1, so you will put 1. So it will be 1s1. So that's how it's going to be for the hydrogen. Now, what about the helium? Helium, we have 2 electrons. Helium has 2 electrons. So this is the first electron. What about the second one? Each orbital maximum in each box which represent the orbital, it is 2 electrons. Cannot hold more than 2. Okay, so I will put the second one, but be careful. How you will put it is very important because they have to be in opposite spin. Spin up, the other spin down. So I will put it and spin down, and that's what we have for helium. This is for helium. Okay, now let's keep going, continue. We have the boron, sorry, lithium. We have lithium has a 3 electron. Now, the first 2 electrons will go to 1s. Now, what about the third one? Can I put it in 1s? No. The maximum of electron in each box, it is 2. Don't put more than 2. So what you have to do in this situation? Go to the next level of energy. You remember the order that we draw it? As I said, just follow the arrow to get the correct order. We have 1s, 2s, and 2p, and 3s, then 3p, then 4s, then 3d, then 4p, and then here we have 5s, and it will be 4d, and it will be 5p, and you will continue. That's the order. Okay, memorize it, do the diagonal rule that we practice with it, like with the arrow, how you will do it. So it's very important to know the correct order. Okay, so here I will start with the 2s. What do we have? 2s. How many electrons left? Just 1. So you will put just 1 electron here. So it will be 2s1 here. And this is the electron configuration for lithium. Sometimes in the question they ask you for the orbital diagram, orbital boxes. You will do it like this. By the way, it doesn't matter to do it like this way. You can do it like this. So you will just put, for example, 1s and 2s from box. 2p, I have 3 orbitals, so you will draw 3 boxes. It's not necessary to show it in this way that I do it. I just try to show you here what is the difference in the level of energy. And be careful, guys. Here, I think there is a mistake. The D, it is 5 orbitals, not 4. Okay, so try always to correct in this slide. Okay, and if they ask you for the complete electron configuration, it will be like this one. That's the complete. Okay, try to practice with some other example. For example, this is for beryllium. That's how it's going to be. Boron, the 5th electron will go to the 2p. And then carbon, the 6th electron will go here. Be careful. Look at here. In boron, we will start to have filled here. Okay, we just have 1 electron, so there is no problem. But in carbon, don't put it here. No, this is wrong. We have to have filled, so we will put it here. Nitrogen, 7. we have to put it here also because we have to do half fill. Then we will start to fill like oxygen, 8 electron. We will put it here. Select the oxygen. We will start to fill. Na, for example. We will put it here in 2p, and then you will go and fill the 3s. So try to practice with some example for the element. Try to choose any element from periodic table and do the electron configuration. By the way, in the canvas, under the page section, we have a dynamic periodic table. You can go back there and check your answer. It will give you that dynamic periodic table, the electron configuration for each element. So always practice with some example and check the answer in the dynamic periodic table. Okay, what else we have here? Noble gas configuration. What is the noble gas configuration? Noble gas configuration, it is a shorthand electron configuration. And instead of writing the complete electron configuration, we have shorthand that's make it easy, faster, get less space to do the electron configuration. Now, first of all, we need to know the noble gases. This is the noble gases: helium, neon, argon, krypton, xenon, radon. Each noble gas are finished arrow or energy level. Noble gas configuration take advantage of this by condensing what you have to write. So look to this example. Helium. It is 1s2, the electron configuration. Helium is a noble gas. Look to the carbon. 1s2, 2s2, 2p2, because carbon 6 electron. So this is the electron configuration for carbon. Now, for carbon, the shorthand, the noble gas configuration, what you're going to do? You will replace this part, which is a common part between helium and carbon. And instead of writing 1s2, you will just put the noble gas, helium, inside a bracket. What left there, you will put it down. So it will be 2s2, 2p2. That's what we have. Now, here in carbon doesn't make any difference, okay? Well, it didn't save a time, but when we will go with the higher atomic number element, no, it will save the time and space, and you will see the difference. So, for example, look at here. I have sodium. What the electron configuration for sodium? It is 1s2, 2s2, 2p6, 3s1. This is the electron configuration for sodium, which has 11 electrons. Now, I need the shorthand. Look at here, guys, how you will deal with that one. Choose the noble gas that's coming before. Choose the noble gas that's coming before the element. So here we will, for example, the first step, choose noble gas coming before the element. Okay? Which noble gas coming before sodium? It is neon. Now, how many electrons for neon? 10 electrons. Neon has 10 electrons. So here you will start to count 10 electrons. This is 2, 4, 6, 10. So that's what we have. Okay? So replace the electron of noble gas by the symbol of the noble gas. Inside bracket, put a bracket in. Inside bracket. Okay, so this is 10 electron of neon. So what we're gonna do, I will put the bracket and we'll replace this electron by neon. What left? Just write it down. 3s1. So this is the shorthand for the sodium. Look at this example also. Arsenic has this electron configuration. Now, which noble gas coming before the arsenic? It is argon. How many electrons for argon? It is 18 electrons. So I will start to count 18 electrons. This is 2, 4, 6, 12, 18. So I will replace this part by argon. I will replace it by argon inside the bracket. What left? Just write it down. It is 4s2, 3d10, 4p3. It is the shorthand, the noble gas notation for arsenic. Okay, now one more things here we have, let's see. The exception to of principle. We have some exceptions. Actually, we have many exceptions, especially when you will go and work with the lanthanide, actinide. But here, we will just focus on this exception, these two exceptions. Whenever we have n minus 1 d, and before it, it is ns. Look at here. If you have 2, and here we have 4. Whenever we have this situation in the electron configuration, we will make it ns1 n minus 1 d5. Guys, if the n minus 1 confuse you, if you have s close to d, we have 2 and 4, we will make it s1 d5. As I said, we have some other exception, but we will just focus on this exception and another exception. If you have s2 d9, we will make it s1 d10. Just focus right now on this exception. Don't worry about the other exception. We have some other exception when we will start to fill the FF orbital. But right now, these two exceptions. Okay. Why this exception has happened? Because the half filled or the full filled, it is more favorable. Okay. Half filled here we have, or full filled here for the D, it is more favorable. So for example, for chromium, this is the regular electron configuration for it. Argon inside a bracket, 4s2, 3d4. But look at here, what we said, if we have this situation, s2d4, we will make it as exception and we will do it as s1d5. So it will be argon inside the bracket, 4s1, 3d5. Always remember, half full is good, and the full, it is the better, of course. That's why we have some exception. So look here. We have this element. What do we have? We have the S, 6s2, and the 5d9. So here, what's going to be? It will be S1 and D10. Look to the kappa. Kappa 29 electron. We will do it here. Now, guys, be careful. This exception happened only between S and D, at least right now. We have some exception between D and F and S and F, but right now, your class just focuses on this exception between S and D, because there is overlapping in the level of energy. They are close to each other in the level of energy, and that's what it's happened. So it's going to be easy for the electron from S to move to D. Okay, anyway, look here for the kappa. 1s2, or let's do it shorthand quickly. Which element coming before the kappa noble gas? It is argon, argon 18, and what we have the 4s 2, 3, D9. Now look at here, S2, D9. So we will do it like this way. So don't leave it like this way, guys. Okay, this is not accepted. It's supposed to be argon and 4s1, 3d10. Guys, just do it when we have s2, d4, do it s1, d5, or s2, d9, do it s1, d10. Other than that, there is no exception right now, at least in your class. As I said, we have many other exceptions, especially when you are working with the higher atomic atoms in lanthanide and actinide, but don't worry about it right now. Okay, I will go through the valence electron quickly also. What is the difference between valence electron and core electron? What is the difference between them? So valence electron are the electron in the outermost principal shell, in the last shell. Shell, guys, not subshell, so be careful. Core electron, it is the other electron inside before the valence electron or valence shell. So look here, silicon has this electron configuration. Okay, now which one is the valence electron? Look to the last shell. Be careful, this is last subshell, the 3p. The last shell, the main shell, the last shell or valence shell, it is the highest n value. Which one is the highest n value? There is the 3s and the 3p. So this is the last shell. How many electrons you have on it? 4. 2 here and 2. So it will be 4 valence electron. The other electron here inside, so it will be called core electron. Look to this example. We have selenium, has this electron configuration for selenium. Which one is the last shell, the valence shell? Look to the highest n value, 4p for s, 3d not, okay, last shell. So the 3d not last shell, and it's just 4s and 4p will be last shell, and we call it the valence shell. And how many electrons we have? 2 and 4 here, 6 electron, 6 valence electron, we call it 6 valence electron. And these in the blue color here, it is the core electron. Valence electron is very important, guys, because it will help us to predict the not predict, but it will help us also to understand the reaction, the bonding between the atoms. So it's very important to know the valence electron. Look here, guys. So there is another way that you can figure out the valence electron. It is from the number of the group. If you remember previously, we talked about the 8 main group. 8 main group. And there is a number with the letter A. 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. Careful, guys. Here, what do we have? We have transition metal. We have inner transition metal. So this not included. I'm talking about 8 main group. Group 1, 2, 3, 4, 5, 6, 7, 8. The number of that group will represent number of a group here will represent the number of valence electron. So for example, if I ask you how many valence electron for oxygen, look to the oxygen. Where is oxygen? It is in 6. So oxygen will have 6 valence electron. How many valence electron for beryllium? Look to beryllium. It is in group 2. So beryllium will have 2 valence electron. Without going back and doing the electron configuration and see the valence shell, from the group number you can decide how many valence electrons. So for example, Cl. This is the Cl. Which group? It is in group 7. So Cl will have 7 valence electron. Neon. This is the neon in the group 8. So neon will have 8 valence electron. So that's how you will figure out the valence electron. Okay. Also, electron configuration in the periodic table. You can use the periodic table to quickly figure out the electron configuration. So, for example, these two groups here, 1A and 2A, we call it S block, the S block, because the last electron will be filled here in S. So this first group will be NS1, S1, NS2, the last electron. I'm talking about the last electron. Here, we call it D block. D block, it is the element that has the last electron filled with the D orbital. Here, we have the F block. F block has the element that's the last electron filled in the F orbital. Okay, and P block, because we have the element has the last electron filled in the P block. Be careful with the helium. Helium, it is S block. Helium has one S2. Okay, supposed to be here. Okay, now be careful, guys. We have here 7 period. 1, 2, 3, 4, 5, 6, 7. That's been here. N equal 1, N equal 2. The row number equal the shell number. N equal 3, N equal 4, 5, 6, 7. Okay. Now, look at here. When we have electron configuration, you can know which row, which period it is. And also, you can know the subshell, which group, and the group number, how many valence electrons. So look here. This is in period or shell number 1. Here, the subshells possibility are these S, P, or D, or F for subshells here. But here we have S. So it will be in the S block. And here, can give you the number of the group, which represents the number of valence electrons. So it will be in group 1. So this one you can say it is the hydrogen atom. Okay, look at here. Lithium. Find the element in the periodic table. Atomic number equal to 3. Now, what is the period? Go back to lithium. Let's see if we have the lithium here. This is the lithium. It's in period 2. So lithium in period 2. How many shell? Number of period equal number of group. Period will give you the number of shell. Represent the number of shell. So it has 2 shell. What is the group number? Go back to this one, lithium. It is in group 1. It will be group 1. How many valence electrons? Because the number of valence electrons equal the number of the group, so it will be also 1. What subshell does lithium have? So look at here. It has the S, so it will be S. What is the electron configuration? 1s2, 2s1. Some type of the question that we could have it. Okay. Boron has atomic number 5. Which row? It is in 2. How many shell? We said it is also 2 because it will be equal to the number of row. Which group? It is in group 3. You can check it in your periodic table. How many valence electron? The number of valence electron equals the number of the group, so it will be 3. What subshell does B have? It is the P orbital, and the electron configuration 1s2, 2s2, 2p1. Okay. Be careful with the D and F, guys. Look at here. Here we have 7 period, we said. So for example, here we have 4s. Here we have 7s. Be careful with the D and F. D will be n minus 1 D, and F n minus 2 D. By the way, guys, the F block element here, this one and this one, is supposed to be here before the 5D or 6D. Okay? Which we call it 4F and 5F. And also give you some idea about the electron configuration for all elements in the periodic table, so it can help you also to practice with some example. Okay, now the last section, the properties, some properties for the element. First of all, we will learn about the atomic size, atomic radius, ionization energy, how many electrons they lose, metal characteristics. Now, all these properties depend on two different things: valence shell, effective of a nuclear charge. Valence shell, it is the last shell that's responsible for the electron to do the bonding of the reaction. What is the effective nuclear charge? Effective nuclear charge, it is the power, attractive power of the nucleus, which has the positive proton, to attract the electron toward it. Okay, now when you will go down in the group, valence shell increase. That means the size of the atom will be larger. And when we will go from left to right in the periodic table, every time we have a new proton, the proton number of proton increases. That means the power of the attraction forces for the nucleus will be higher. So effective of nuclear charge will be higher. Okay, I will give you this trend in general that can help you to predict or make a comparison, guys, for the size of the atom. Going down, size will increase. Going down, size increase. Going from left to right, size decrease. In general, going in this direction, the size will increase. So for example, if I ask you which one is a bigger, oxygen or carbon, according to this trend, the size decrease when we will go from from left, to right. Carbon will be bigger than the oxygen. If I ask you which one is bigger, lithium or potassium, for example, according to the trend that we have it here, going from top to the bottom, this size increase. So I can say potassium, it is bigger compared to the lithium. And that's how you will make your comparison. Okay, so look at here. For example, if I ask you, don't look to the number. If I ask you sulfur and, for example, citron, which one is bigger? Going in this direction, size will be largest. So I can say strontium, it is bigger than the sulfur. Here we have example. You can practice with it in the PowerPoint slides. And let's look for ionization energy and other properties. Ionization energy, it is the opposite to the atomic size. Going from the top to the bottom, ionization energy decrease. So it will be the opposite for the size. Going from left to right, ionization energy increase. And in this direction, the ionization energy will increase, will be the highest. Also, we have some example here. You can practice with it with the PowerPoint slides. Okay, one more properties, the metallicity properties. In general, guys, look at here. Going from the top to the bottom, the metallicity will increase. Metallicity increase. Going from left to right, metallicity will decrease. And also, here, going in this direction, metallicity will increase. So for example, if I ask you which one has more metallicity properties, oxygen or carbon? Oxygen or carbon? What do you think? According to this trend, going from left to right, the metallicity decrease. That means carbon more metal compared to the oxygen. Both of them non-metal, it is fine, but which one has metallic properties, metallic character? Carbon will be more metal compared to the oxygen. These the important things in this chapter. Try to review the PowerPoint slides before seeing this video, and also try to practice with some more example before starting doing the homework. Just one more thing here, I just want to talk about it because it will help us also to start with the next chapter for Lewis structure. Stability. Stability mean non-reactive or low energy. It's based on filled shell. Whenever we have element with the filled shell, that one will be stable. Doesn't need to lose or gain electron to achieve the stability. It's already stable and filled, so it doesn't lose or gain electron. The element in the noble gases group, this element, has a filled shell, and they tend to stop reacting. They tend to stop losing or gaining electron. They don't need to lose or gain electron. Other element will try to have the same number of electron like the noble gases. Some of them will achieve the goal, some not. The element in the main, in the 8 main groups, that we already talked about it, mostly they will achieve the goal and have the same number of electron like noble gases by losing or gaining electron. But the element in transition metal group or inner transition metal, lanthanide and actinide, most of them, they don't achieve this goal. They achieve something else to be more stable. So look at here. Here, many atoms want to fill shell like noble gases, so they gain or lose electron. So look here, you can find how many electron each element need to lose to be stable. So for example, calcium. Look to the calcium. This is the calcium. Now calcium need to lose or gain electron. Or you can ask another question. Calcium will form positive ion or negative ion, and how many charge? You will compare the calcium with the noble gas that's coming, with the noble gas that's close to it, not necessary to be coming before it. Compare the element with the noble gas that's close to it. So calcium, which noble gas close to it? It is argon. Now calcium has 20 electrons, argon 18. Calcium wants to lose 2 electrons to be similar like argon. So calcium will lose 2 electrons, will have the calcium 2 positive, and that's for similar to argon. Barium. Look to barium. Barium 56, close to xenon, the noble gas, 54. Barium need to lose 2 electrons to have Ba2 positive and be similar like xenon. Aluminum. This is the aluminum. The noble gas that's close to it, it is the neon. Okay, so aluminum need to lose 3 electrons to have aluminum 3 positive and be similar like neon. Okay, indium and 49, it close to xenon. Okay. Indium. So just 1 minute, sorry guys. Here we have